All right, hey folks, we're going to give this another shot here and see if this works out. So we're going to move on using velocity and time graphs to find acceleration. At any point, just feel free to pause, jot down what's here for like a title or maybe the notes that are kind of throughout the whole thing. Play it back through if you need another go at it, just to kind of get an understanding of what's going on, and we'll see how we make out. This kind of sums up a lot of separate concepts that we've been talking about, but really it's not a far jump into anything else, it's just a different way to look at it. So to start off, I'd probably get you to jot down the title, what's up here, using velocity time graphs to find acceleration. And then I have a little graphlets here, and what I will do is get you to take a second and determine the average acceleration in each segment. So keep in mind, we've talked before about kind of how to go through and find slope. And so we have a velocity time graph here, and we've done these before with distance time graphs. We're just going to take a different look at it and talk about it in terms of AAV is equal to VF minus VI over T. So for each segment, take a look at A, find out what its final velocity is minus its initial, and divide it by the time interval. And then come up with what the accelerations look like for each one. So pause, give it a try, and then just hit play when you're ready. I'll go to the next slide and kind of work through what each of those look like. So segment A, if we start off with that one, we've got average acceleration is equal to, and then we have our VF minus VI over T. So AAV is equal to, and it's 30 meters per second minus 10 meters per second, all divided by 5.0 seconds. So AAV works out to give us 30 minus 10 is 20, and 20 divided by 5 gives us 4 meters per second squared. If I take a look back, it does say south for the direction. So if I go back in here, I should probably add in that we're traveling south. Okay, for the B one, when we take a look at our graph, we have AV, VF minus VI over delta T again. So AAV is equal to, now VF minus VI, it's the same number in each one. It's 30 meters per second. So really it doesn't matter what the time unit is on the bottom, because this thing is going to work out to give me 0 meters per second squared for an acceleration. So what does that really tell you in the whole thing when we go back and we take a look at it? Well, B is a flat line, and so the velocity never changes, it stays constant. And if it's a constant velocity, that means that there is no acceleration. So a flat line on a velocity time graph indicates constant speed, which means that there's no acceleration. So we could see A increased, B was a constant speed, no acceleration, and then we can take a look at C and go through that one. So AAV is equal to VF minus VI over delta T. AAV is equal to 0 meters per second minus 30 meters per second over top of 20 seconds minus 15 seconds. And so AAV is equal to minus 30 meters per second over top of 5 seconds. So AAV gives us negative 6 meters per second squared. Now remember, our direction here was heading south, and we talked about this before. If I've got a negative acceleration heading in one direction, really a way that I can write that is just to flip the sign. We make it into a positive, because really it's indicating that it's going at a positive acceleration in the other direction. So that kind of gives you an idea of how to calculate using average acceleration, calculating each of the slopes. Okay, so this is going to let us jump into the next part. And so the next part is using position time graphs to find acceleration.